In this video, we'll discuss ventilation part 2. We'll discuss minute ventilation, alveolar ventilation rate, and control of ventilation. When you've done studying the topic, you should be able to define minute ventilation, write the formula to determine minute ventilation, and when given the appropriate measurements, determine the minute ventilation of an individual. In regards to alveolar ventilation rate, you'll be able to define what alveolar ventilation rate is, write the formula to determine the alveolar ventilation rate, and when given the appropriate measurements, determine alveolar ventilation rate. Minute ventilation is simply the amount of air which can be exchanged in 1 minute. The amount of air exchanged in 1 minute. When I say exchange, what I mean is inspired and expired. How much air you breathe in and breathe out in 1 minute. The formula is for minute ventilation rate equals the frequency of breaths times the volume of that breath. So if your frequency is 12 breaths per minute, and let's say we'll measure tidal volume of 500 mils per breath, the minute ventilation would then be 6,000 mils per minute. Simply the volume times the respiratory rate. During the lab exam, I'll give you the volume, I'll give you the respiratory rate. You'll have to remember the formula to determine what the minute ventilation is. The alveolar ventilation rate is a bit different. Whereas in the minute ventilation, which what we just wanted to find out how much air would come in and leave during the respiratory cycles for a minute. However, when you look at the respiratory tree, a bit bigger here so you can see easier. Respiratory tree. Here's your lung tissue. When you inhale, the air which comes in, some of the air which comes in will not make it to the alveoli. Therefore, you cannot use that air to ventilate the alveoli. So dead air has to be taken accounted for. Normally, this is 150 mils, and it's pretty consistent. So, the minute definition of alveolar ventilation rate is the amount of air which exchanges in the alveoli every minute. And a similar formula to the minute ventilation rate, frequency times volume minus 150 mils. 150 mils refers to 150 mils in your brachial trachea, which does not make it to the alveoli. So let's say you have a frequency of 12 breaths per minute, and we're using tidal volume again. You have to subtract that airspace that's not being exchanged. So you knew 12 times 350. Now I know your math. 350 times 12, that's 700. 350 4,200 mils per minute. So the definition of alveolar ventilation rate is the amount of air which actually ventilates the alveoli. The formula is the alveolar ventilation equals the frequency times the volume minus 150. This is constant. That is what is in the branchial tree. Write out the formula, and there's your answer. The third aspect is control of ventilation. And when you finish studying this topic, you'll be able to describe which parts of the central nervous system are responsible for control of ventilation. You'll describe the primary factor which increases the ventilation for a healthy individual. You'll describe the primary factor which increases the ventilation for individuals with long-term COPD. Describe why placing an individual who has COPD under 100% oxygen is a bad idea. You'll then define the following terms: hypercapnia versus hypocapnia, hyperventilation versus hypoventilation, and finally explain the relationship between ventilation, CO2 levels, and hydrogen levels using carbonic acid dissociation formula. Begin. CNS, the two main parts involved in the central nervous system, pons, and the medulla, base of the skull. If either of those are damaged, you'll then have problems initiating the breathing reflex. You don't need to go into more detail as to how the process works, but do be aware where that process occurs. Number 2, the primary factor which causes an increase in ventilation for healthy individuals is high CO2 levels. Remember from Fick's law, CO2 has a diffusion constant 20 times greater than oxygen does. Because of that, oxygen stays fairly constant, but the CO2 levels will change pretty quickly. Thus, if your blood levels of CO2 get too high, you're going to increase your ventilation. Decreased ventilation will blow off your CO2. That's with increased ventilation. So as you hyperventilate, you'll get rid of the CO2. Now, for a individual COPD, that process does not work. The reason that process works in the first place, in the brain, CO2 comes across into the brain, to the cells, then it goes to the carbonic acid formula to form hydrogen. And that is actually what causes the central receptors to make you start breathing faster or deeper to get rid of the CO2 to shift back out and lower the hydrogen concentration. However, a person who has chronic COPD, the brain, knowing this is dangerous, will secrete bicarbonate. The result is that's neutralized. So although when CO2 levels in the blood may still be high, that is no longer reflected in the brain and no longer cause to inhale. So for an individual with COPD, the primary cause of breathing is low oxygen levels. When they get less than 50% normal, at that time, the breathing reflex will begin and the individual will start breathing. One of the questions asked is if you have a client with COPD, should you put them on 100% oxygen? Well, initially, you think yes. Let's say here's the oxygen level here. And at 50% is when they start to breathe. And when they come into the clinic, let's say the level is down to 45%. If you give them pure oxygen, that level is going to go much higher than that. So instead of having 50% oxygen in the blood as they've been expecting, they now have a higher level of oxygen. Because of a higher level of oxygen, since they're now above this, the impetus to breathe is no longer there. There's no ventilation occurring. Because the brain's saying, wait a second, we have more than 50% oxygen, so we're good to go. So ventilation stops. The problem is, even though the ventilation is no longer occurring, cellular respiration is still occurring. The byproduct of that is hydrogen protons, which means as you're no longer ventilating, this individual's blood will become acidosis. Now you have a whole new set of problems on your hand. Because he's no longer breathing, there's no way to blow off carbon dioxide, you can't shift the formula back to the left, and you're now in a state of acidosis. So in this case, an individual, you probably give them probably 55-60% oxygen, get up near this area here, and that's all you give them. The terms you need to know: hypercapnia means high CO2 levels. Hypocapnia means low CO2 levels. Hyperventilation refers to the fact that you're breathing much faster and deeper, compared to hypoventilation, which the rate and depth are decreasing. And finally, the correlation with the formula: CO2 plus H2O, H2CO3, H plus HCO3 minus. If your CO2 levels go up in the blood because you're not breathing as rapidly or deeply as you should, not blowing off carbon dioxide, if that goes up, you know this will go up. If carbonic acid goes up, hydrogen concentration will go up also. If that goes up, your blood will now become a state of acidosis. On the other side, if your CO2 levels decrease because you're hyperventilate, this goes down, this will go down, this goes down. As the hydrogen concentration goes down, your pH goes up, and now you state of alkalosis. And that concludes